For most of modern history, electricity demand followed a rhythm utilities understood. Growth was linear. Peaks were seasonal. New loads arrived slowly enough that planners could model them, regulators could approve infrastructure, and engineers could build transmission years ahead of need. Power systems evolved around households, factories, and cities, whose behavior changed gradually. Artificial intelligence does not fit that pattern. AI is not a consumer load. It is not a marginal increase in electricity demand. It is an industrial-scale, always-on, latency-sensitive energy sink that grows exponentially rather than incrementally. And unlike traditional heavy industry, AI does not naturally co-locate with rivers, mines, ports, or fuel supply. It co-locates with fiber, data, talent, and capital. That single shift changes everything. What we are witnessing is not simply rising electricity demand. We are watching a mismatch between how fast intelligence scales and how slowly infrastructure adapts. And the global power grid, one of the most complex machines humans have ever built, is starting to show stress fractures. Data centers that once consumed 5 or 10 megawatts now plan for hundreds. Hyperscale AI campuses are discussing gigawatt-class demand as a design requirement, not a distant ambition. These are not speculative numbers. They are already appearing in utility interconnection requests. And utilities are responding with a phrase that has quietly become the most dangerous sentence in the energy transition. We don't have capacity. In Northern Virginia, the world's densest data center cluster, grid congestion has become a strategic constraint. In Ireland, regulators have restricted new data center connections outright. In parts of the United States, AI developers are being told that new transmission may take a decade, if it is approved at all. This is the same friction green hydrogen producers, advanced manufacturers, and electrified industrial projects have faced for years. But AI arrives with more capital, more urgency, and far less tolerance for delay. AI doesn't wait for grids. It routes around them. And once that reality sinks in, a radical idea begins to resurface. Not because it suddenly became cheap, but because Earth-bound energy systems are approaching their functional limits. Space-based solar power has existed for decades as a technical curiosity. Engineers understood the physics, economists dismissed the cost. Policymakers ignored it entirely. It lived in the category of interesting but unrealistic. AI changes that categorization. Not because space solar is suddenly economical in a conventional sense, but because the definition of economic viability shifts under system stress. When grids are congested, land is contested, permitting is slow, and reliability is paramount. New criteria dominate decision-making. Availability beats efficiency. Time to deploy beats elegance. Reliability beats theoretical cost curves. Space solar offers something terrestrial energy struggles to guarantee: continuous generation unconstrained by land, weather, or local politics. In orbit, solar panels do not sleep. They do not experience night cycles, cloud cover, seasonal swings, or grid curtailment. The capacity factor of space-based solar is fundamentally different from anything on Earth. That alone forces a reevaluation, not as a replacement for terrestrial power, but as an escape hatch when the grid becomes the bottleneck. But generation alone is never the full story. The true constraint in modern energy systems is not how many electrons can be produced, but how energy moves across space, time, and systems. This is where most public debates fall apart, because they confuse generation technologies with system performance. On Earth, electricity must travel through transmission lines that are already overloaded, politically contested, and slow to expand. Even when generation exists, delivery often does not. Curtailment is not a failure of generation. It is a failure of systems integration. In space, the problem flips. Energy can be generated continuously, but it must be converted, transmitted, and integrated into terrestrial infrastructure. That integration problem is where hydrogen becomes relevant, not as a slogan, but as physics. Hydrogen is often framed as inefficient, and by narrow electrical metrics, that critique is accurate. But energy systems are not optimized for efficiency alone. They are optimized for flexibility, buffering, and survivability. Hydrogen excels where electricity struggles: long-duration storage, transport across domains, and decoupling generation from use. It acts as a translation layer between systems that cannot directly interface. In a future where energy may be generated in orbit or other non-terrestrial domains, hydrogen offers a pathway to make that energy usable on Earth. Whether conversion happens in space, at receiving stations, or within industrial hubs, hydrogen provides a mechanism to absorb, store, and dispatch energy independent of grid congestion. This reframes hydrogen's role entirely. It is not competing with batteries for short-term grid balancing. It is not trying to replace electricity. It is acting as infrastructure glue, the same role LNG, ammonia, and synthetic fuels already play in global energy logistics. Once you understand that, the space-solar discussion becomes less about science fiction and more about systems architecture. AI exposes the weakness of Earth's energy assumptions. The grid was built around distributed consumption, predictable growth, and centralized control. AI introduces concentrated demand, explosive scaling, and private capital that will not wait for public processes. This collision creates a new class of energy decision-makers. AI developers are not utilities. They are not governments. They are not patient infrastructure planners. They are optimization engines seeking reliability above all else. And when reliability becomes the dominant variable, the energy stack changes. On-site gas turbines reappear. Private microgrids proliferate. Nuclear microreactors move from theory to procurement discussions. Hydrogen enters as a storage and dispatch layer, and space solar stops sounding absurd. Not because it's easy, but because everything else is constrained. This is the same pattern seen throughout industrial history. When existing systems reach their limits, previously uneconomic solutions become necessary. Railways replaced canals. Pipelines replaced railcars. Subsea cables replaced satellite links for data. Space solar is not a green dream, it is a system's response to a bottleneck. And AI is the stressor revealing that bottleneck. The key insight here is that energy transitions are not driven by ideology. They are driven by constraint relief. Technologies win not because they are perfect, but because they solve the problem others cannot. Wind and solar solved marginal generation. Batteries solved short-term variability. Hydrogen solves temporal and spatial decoupling. Space solar may solve planetary constraints, but only if the system demands it. This is why the most important question is not, is space solar cheaper? But what happens when the grid cannot deliver power at all? Once the answer to that question becomes projects stall, economics change rapidly. AI developers cannot afford idle compute. Downtime is existential. Delays are unacceptable. Energy that exists beats energy that is cheap but unavailable. This is the same dynamic that has quietly reshaped hydrogen project outcomes. Many projects fail not because electrolyzers don't work, but because utilization assumptions collapse. Power is intermittent. Infrastructure arrives late. Demand contracts are misaligned with supply timelines. The physics works, the system fails. AI is now stepping into that same failure mode, but at scale and speed we have never seen before. Grid interconnection queues stretch into years. Transmission approvals face lawsuits. Land use conflicts intensify. Even renewable heavy grids struggle with reliability under concentrated load. Space solar bypasses many of those constraints by definition. It does not require land acquisition. It does not face local opposition. It does not depend on regional weather patterns. It does not compete for transmission corridors in the same way. Its challenges are different. Launch costs, orbital construction, maintenance, and energy transmission. But those challenges exist in a domain where engineering timelines are increasingly compressible. Launch costs have fallen dramatically. On-orbit assembly is advancing. Autonomous robotics is improving. AI itself accelerates design and optimization of complex systems. Ironically, AI may be the force that makes space solar technically viable, even as it creates the demand that makes it necessary. This feedback loop is crucial to understand. AI increases energy demand. That demand stresses grids. Grid stress forces alternative architectures. Alternative architectures rely on advanced engineering. Advanced engineering is accelerated by AI. Hydrogen fits into this loop as a stabilizer. It absorbs volatility, it provides storage. It enables energy to be produced where it is easiest and used where it is needed. In this context, hydrogen's inefficiency becomes less relevant than its optionality. Optionality is the ability to adapt when conditions change, and in the coming decades, conditions will change rapidly. Subsidies will fluctuate, political priorities will shift, climate events will intensify, AI workloads will migrate, infrastructure will lag demand. Energy systems that survive are those that can flex under pressure. That is the competitive edge test. If subsidies disappear, prices fall, utilization misses targets, and timelines slip. Which systems still operate? Pure grid dependence fails that test. Over-optimized, single-path systems fail that test. Energy stacks with redundancy, buffering, and domain flexibility pass it. Space solar, hydrogen, nuclear, and localized generation are all expressions of that same survivability logic. None of them are silver bullets. Together, they form resilient architectures. This leads to a broader conclusion about the future of energy and intelligence. By the 2030s, we are likely to see a bifurcation. Consumer energy remains grid-bound, politically managed, and cost-sensitive. Industrial intelligence, AI, robotics, autonomous systems moves toward bespoke energy ecosystems, optimized for reliability rather than public consensus. These ecosystems will look less like traditional utilities and more like logistics networks. Energy will be generated, converted, stored, and dispatched with the same intentionality as data. Hydrogen becomes a carrier, not a debate. Space solar becomes a node, not a novelty. Grids become one layer among many, not the foundation of everything. The transition will not be clean or uniform. There will be failures, false starts, and expensive lessons. But the direction is clear. AI is not breaking the grid because it is reckless. It is breaking the grid because the grid was never designed for exponential intelligence. And once that truth is accepted, the question is no longer whether space solar is realistic. The real question is how many other ideas dismissed as too complex become inevitable when Earth's energy systems hit their limits. We are entering an era where energy is no longer just a commodity. It is infrastructure under stress. And systems that can survive that stress across time, space, and domains will define the future. AI didn't create the problem. It just revealed it faster than anyone expected.